Okay, in this video, we'll be talking about the dielectric inside the capacitors. What is a dielectric? A dielectric is a substance that you insert in between the capacitor so that you can increase the capacitance of the capacitor. So for example, this is an air-filled parallel plate capacitor. There's nothing in between the parallel plates. But then you insert something in between the parallel plates. Okay, so this substance is called a dielectric. A dielectric is an electrical insulator. A dielectric should have very little or no free electrons at all. A dielectric prevents electric current flowing through it. A dielectric becomes polarized under external electric field. Okay, so now this is a microscopic view of the dielectric. That means that you are looking at the individual molecules. So now let's say this parallel plate is positively charged and then this is negatively charged. There is an original electric field which is indicated by the blue color here. But then, this is positively charged. The molecules of the dielectric will be polarized. That means that this will have negative charge and then this will have positive charge. This is negative charge, this is positive charge, and the process repeats. But then, the induced charge in the dielectric should have a smaller amplitude. That means that the magnitude of the induced charge should be smaller than the charge of the parallel plate. But I will show you later on. Okay, the blue line indicates the original electric field, and then the red line shows the reverse electric field. And then the net electric field would be this minus this, so that you know the overall electric field will decrease. Explain briefly in microscopic view how the presence of a dielectric material between a parallel plate capacitor can increase the capacitance. For an isolated charge capacitor, when a dielectric is inserted in between the parallel plates, the polarization of the dielectric material occurs. The dielectric molecules will become polarized to form electric dipoles. The electric dipoles align themselves along the electric field between the parallel plates to produce a reverse electric field E'. Okay, the E' is the red color one. The original electric field is the blue color one. Okay. I often denote the reverse electric field by E'. Then the net electric field between the plates is reduced. This is the net electric field, which is this minus this. And then you know that when the net electric field is reduced, the potential difference between the plates is also reduced. Okay, by using this formula. The charge remains constant for an isolated charge capacitor. Okay, you only use the principle of charge conservation for an isolated capacitor. That means that if the capacitor is charging or discharging, then you cannot say that the charge is constant. I will show you how the charge varies with time later on in the CR charging circuit and also CR discharging circuit. Okay, so when potential difference decreases, which is V decreases, and then Q is a constant, C will increase. So you say that the capacitance C increases. Okay, this is how the dielectric increases the capacitance. Explain briefly in microscopic view how the presence of a dielectric material between a charging parallel plate capacitor can increase the electric potential energy of that capacitor. Just now we are talking about how the dielectric can increase the capacitance. Now we are talking about how the dielectric can increase the electric potential energy of the capacitor. Okay, for a charging capacitor, when a dielectric is inserted in between the parallel plates, the polarization of dielectric material occurs. The dielectric molecules will become polarized to form electric dipoles. The electric dipoles align themselves along the electric field between the plates to produce a reverse electric field, and then the net electric field is reduced so that the potential difference between the plates is also reduced. Until now, this is exactly what you have learned just now. But then, from this point onwards, the explanation slightly differs. Okay, for a charging capacitor, while the capacitor is still charging, the battery will charge the capacitor back to the initial potential difference between the plates. And so that while the battery is charging the capacitor, you know that the charge in the capacitor increases, so that the energy stored inside the capacitor will increase also. Okay, now please find the magnitude of the induced charge Q prime in a dielectric. You know that the charge of the parallel plate is positive Q and negative Q respectively, and then now you want to find the induced charge Q prime of the dielectric. Okay, without the dielectric, that means that there is now only air in between the parallel plate capacitor. This is what you would get for the Gauss law. E0 is the initial electric field contributed by the parallel plates. And then with the dielectric, the electric field changes, and then the net charge enclosed by the Gaussian surface also changes. The relationship between the electric field now with the original electric field is this. And then E0 equal to Q over A epsilon naught. You substitute this inside here, and then you can arrive at this equation. That means that the induced charge is equal to the charge of either plate of the capacitor times 1 minus 1 over epsilon r, where the epsilon r is the dielectric constant, which is also the relative permittivity. For example, the epsilon r of the paper is 3.7 and the epsilon r of water is equal to 80. So you know that epsilon r of dielectric is larger than 1. And then from this equation, 1 minus some non-zero value will have a value of smaller than 1. So you know that the magnitude of the induced charge is less than the charge of either plate of the capacitor. So now assume that you use metals to be your dielectric, then what will happen? Metals are the most polarizable materials in nature. So if you use metal as dielectric, then by using this formula, you know that the amount of the induced charge is exactly equal to the charge of either plate. So now there is no net charge because Q minus Q prime is equal to 0. So there is no net charge inside the capacitor, and then you will say there is no energy stored in the form of electric field. And then by using this formula, when you know that Q minus Q prime is equal to 0, you also know that the electric field will equal to 0 for sure. Let's do a question. A parallel plate capacitor is separated by airspace of distance 18.5 mm. An electric supply of 12 volt is then connected to the capacitor, and the charge stored inside the capacitor is 2.46 microcoulomb. A dielectric with dielectric constant of 3.06 is then inserted into the airspace between the plates. Please determine the electric field between the plates with air space. E equal to V over D. V is the potential difference between the plates and D is the separation between the plates. Find the capacitance of the plates after the dielectric is inserted. Before the dielectric is inserted, the original capacitance is like this. But now after the dielectric is inserted, the capacitance now becomes this one. So you know that when the dielectric is inserted, the capacitance increases. Calculate the increase in electric potential energy stored inside the capacitor before and after the dielectric is inserted. Before the dielectric is inserted, the energy is like this. After the dielectric is inserted, the energy is like this. So you know that the overall energy of the capacitor also increases. And then the increase in the electric potential energy is the difference between the two. Charges can be induced on a dielectric surface because the molecules in a dielectric can be polarized. Alright. Charge carriers in dielectric are electron-hole pairs? No, dielectric should be an insulator, so there should be no charge carriers. Electric field cannot pass through the dielectric? No, the electric field can pass through the dielectric. Okay? The electric field can pass through the dielectric. Charges in the dielectric can move freely. Dielectric is an insulator, and therefore the charges cannot move freely. You can only induce the charges. That means that the charges cannot get out of the individual molecules. You cannot say that the positive charge here will move to here. No, they cannot move anymore because the dielectric is an insulator. A parallel plate capacitor with dielectric is shown. The charges on the capacitor plates are positive Q and negative Q respectively. Which statement is not true about the capacitor? The electric field within the dielectric is uniform. Okay, so now first, the original electric field can penetrate through the dielectric, and then when the electric field is penetrating the dielectric, you know that there is a reverse electric field. And then the reverse electric field is only within the dielectric itself. That means that I cannot draw the reverse electric field in these spaces, okay? Because I know the reverse electric field is only within the dielectric, okay? And so, the electric field within the dielectric is uniform. Yes, because the lines are uniformly drawn. So I know that the electric field here is equal to the electric field here, 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 and here. So within the dielectric itself, the electric field must be uniform. Okay, so the net electric field is equal to this. The electric field between the plates is dependent on the net surface charge densities. Yes, you know that from this formula, which is the electric flux is equal to EA equal to Q minus Q prime over epsilon naught. You know that the net electric field is equal to Q minus Q prime over A epsilon naught. Q minus Q prime is the net charge enclosed by the Gaussian surface. Q minus Q prime over A is the net surface charge density. Okay, so you know that the electric field between the plates is dependent on the net surface charge density. The induced charges on the surface of the dielectric are equal in magnitude to the charges of the capacitor plates. No, Just now you know that Q prime equal to Q bracket 1 minus 1 over epsilon R. So you know that the magnitude of Q prime should be less than Q. So you know that the induced charges should be less in magnitude to the charges of the capacitor plates. The electric field due to the induced charges is in the opposite direction to the electric field due to the charges on the capacitor plates. Yes, the original electric field is from here to here, and then the reverse electric field is from here to here, so they are opposite directions. A capacitor with an air gap between the plates is connected to a battery. The battery is then removed from the capacitor. When you saw this sentence, you know that most probably you will use the principle of conservation of charge, okay? Because the capacitor is now an individual and isolated capacitor. A dielectric is then used to fill in the air gap between the plates. Which statement is true about the capacitor with the dielectric? Okay, so you use the principle of charge conservation. You know that the charge on the capacitor before dielectric is inserted is equal to the charge on capacitor after the dielectric is inserted. And then so you say that the charge stored inside the capacitor remains constant. Okay, C equal to epsilon R epsilon naught A over D. When the dielectric comes into the capacitor, ER increases. And then you know that C also increases. The electric potential energy of the capacitor is this formula, and also this formula, and also this formula. Now you know that because the charge is a constant, so you should use this formula. Because you know that Q is a constant, and then C increases. And then when C increases, U decreases. So you know that the energy stored inside the capacitor decreases. When there's dielectric, there's reverse electric field, and then the net electric field decreases, so that the potential difference decreases. Okay, so the electric field strength between the plates decreases, and then the potential difference across the plates of the capacitors decreases. A parallel plate capacitor is initially charged by a battery, and then the battery is then disconnected. When you saw this phrase, when you saw the battery is then disconnected, you know that the capacitor is now an isolated capacitor, and that's why you can use principle of conservation of charge. Okay, I repeat one more time. If the battery is charging the capacitor, or if the capacitor is discharging through a circuit, then you do not use this principle of conservation of charge anymore. Okay, only when the capacitor is isolated, only then you use this principle. When the dielectric is removed from the charged capacitor, then what will happen? The charge inside the capacitor remains constant, okay, because it's an isolated capacitor. So you use principle of charge conservation. Okay, C equal to epsilon R epsilon naught A over D. When there's dielectric, epsilon R increases, but then when the dielectric is removed, epsilon R decreases, and then when epsilon R decreases, C also decreases. The total capacitance decreases. When there's no dielectric, there's no reverse electric field, and then the net electric field increases, and then the potential difference increases. Okay, so the potential difference between the plates increases, and then the electric field strength between the plates increases also. So now the energy stored inside the capacitor has these three formulas, and then when Q is a constant, and then you know that C decreases, then you use this formula instead of this and this. Okay, when Q is a constant because of the charge conservation, and then when C decreases because the dielectric is removed, U increases so that you know that the energy stored inside the capacitor increases. Okay, the answer is this. A parallel plate capacitor in a vacuum is charged, and then it stores an energy U. If the capacitor is then filled with a medium of relative permittivity epsilon R and it is charged with the same potential, what is the energy stored in the capacitor? Okay, so now that you know the V is a constant because it stays that same potential. So you know that V is a constant. So you have three formulas for the energy stored inside the capacitor. May I know which is the formula that you prefer to use? Of course, it's this formula because V is a constant, and then you now know that C equal to epsilon A over D when the dielectric is absent. When the dielectric is present, then it is epsilon R epsilon naught A over D. So you know that the energy stored now is equal to epsilon R times the original energy. Okay, so the answer is this. Always make your wise decisions when you are choosing which formula to use for your energy of the capacitor. When Q is constant, then most probably you use this formula. When V is constant, then of course you use this formula. Okay? A parallel plate capacitor is fully charged when an insulator is inserted into the space between the plates of the capacitor. The energy stored inside the capacitor decreases by 73%. What is the value of the dielectric constant of the insulator? So now, again, there are three formulas to be used for your energy of the capacitor. Which one do you prefer to use? So now you see, the charge is constant. Why do you know the charge is constant? Because he said that the parallel plate capacitor is fully charged. So you know that when the capacitor is fully charged, the charge is already a constant because he cannot get more charges. Alright, so when Q is constant, then of course you use the formula U equal to Q squared over 2C. Okay, the energy decreases by 73%. That means that now there's 27% of the energy remains. And so you know that when Q is constant, U is inversely proportional to C. Okay? And then by using this formula, you can know the value of the dielectric constant. We also call the dielectric constant as the relative permittivity of the medium. Okay? The relative permittivity of the dielectric itself. Okay? So in the next video, we will be talking about the capacitors connected in series and also in parallel. Thank you.